Okay, so this recording is in lieu of, I started the meeting at for students to do this review on at 9:30 and waited 30 minutes to allow students to come in and actually, ask questions, get clarity as to what they need to do to be successful for the next quarter, the remainder of the quarter. So let's go through a problem real quick. Very old problem on February 5th. Again, I'm going to post this today because this is a problem a lot of you guys shy away from. So I'm going to post it again today, but it'll be for credit. And I'm not using the same values. All right. So you can go back in time and actually do this problem, get credit for it. And then on top of that, this is for my physics students, physics periods 3 and 4. You can actually look at today's posting for the do now, and it'll be this problem, but with similar values, but not exactly the same. Okay. So with all that said, let's go to, because this is a lengthy problem, it's worth a lot of credits from while I'm doing that. Where are we at? We come, I want to say this is a converter. I want to be able to start a Google Doc. I get this Zoom button keeps scrolling down on me. All right, there. So I'm gonna start me a new Google document. And I'm going to start blank. There we are. We're gonna call this, you always want to get in the habit of naming your documents for electromagnetic or magnetic induction. And this is for today. So we're gonna do our original thing is what? Your header, right? So it's Mike Tyler. And that's what I'm putting for my name for your own observation, but you should be putting your name there. And then, of course, what else are we supposed to put? Well, the date. Well, today is 10th of April, and it is 2020. Period. Well, we're going to put credit recovery for this, but this is mainly, well, I should put physics because that's what this is geared towards, the physics students. All right, so physics, let's say third. If you have 4, if you put 4. And then we need the problem. So let's go back for a second. And I translated this because a lot of you guys said you did not have binary converters. So we're going to take this problem here. And we're going to put the problem inside of our Google Doc, which is our report. Okay, now with that said, this hint will usually come from the physics textbooks we have in our classroom, but with this, current situation, it's kind of difficult. So that's why I'm doing these videos to help you through it. Again, I waited 30 minutes earlier for students to log in. I guess, times conflict, whatever the case may be. So I just want to cover at least one problem. And if, they gain momentum, those students who may catch this video, because I'm going to later post on the SB, log in. That'll be a time we can work on Play-Doh. That'll be the time we can discuss problems that's giving you the most difficulty. You just, these last 2 days of the quarter, make them successful. All right, so let's continue. We're going to tweak the values because, again, I don't want to do the same exact problem for you. Okay, so my values are going to be 2.57, and that'll be in centimeters. That's fine. And what else we got? We have the Teslas. Okay, so we are not going to use that amount. We're going to use actually 526. And then we have what else? Well, the degrees. I also changed those a little bit on you. So it's going to be 2.45. And what else we got? I'm going to change this to 37.6. Next is 68.4. And lastly, it's going to be about 97.6. Okay. So with that said, what we're going to now do is I'm going to set it up, and I'm going to try to post this video in 2 sections. First section is going to set you up. The next section will be how do you do the calculations, all right? But let's get through the basics. So what equation do you utilize? Well, we talked about this before, right? And I don't know if I could pull it up for you. I can't. So I got to retype it. So let's start with the equation. And I covered this in the last video when we're talking about electromagnetic induction. We have angles and cosine and so on and so forth. So what was that equation before? For the definition, I should say. Induction. So what do we got? Looking at this here, this is what we're exactly talking about. In terms of Faraday, we talked about the Tesla self-driving car, but we're looking for the definition in terms of math, not meaning. Let's see what we got. See, this is good here too. But what does all that mean? So we talked about flux. Look that up. Maybe that's how I found it. Flux equation. I think it's magnetic. Here we go. Found it. So if you see here, you have flux, which I talked about before, which is this little circle with an I crossed through it. That's exactly what I'm referring to each flux calculation as, basically that symbol. And those things are like, how do I type that? That's why I want you to know what it's called so you can actually understand it. Wow, there we go. Found a great representation. I always love hyperphysics over the years. All right, so let's go through it. We're going to start with the flux here, which is equivalent to the B field multiplied by the area. But there's also a situation when you have angles involved, right? So this is the basis of it, but let's go a bit, further. There's going to be a cosine involved, and it didn't show you this one in the way I wanted it to, but it was close enough. So there's always an angle that's going to be included in the calculation we're about to do. We have 4 angles, so that means we have to do the calculation 4 times. So let's get involved, right? Magnetic flux is measured in Tesla meter squared. And then you have an equivalence of the B field, call this vector B. This is usually when you have a line going across the top of the B value, multiplied by, and what is that measured in? That's my apologies. Teslas. So multiplied by our area. And area is an actual equation in geometry that you have to make yourself familiar with again. So that's A area for area is equivalent to pi times our radius r, and that's going to be squared. Okay. So let's just keep moving. We have also, and this is just a conceptual view of it. This is going to be multiplied, but like I said, trigonometric value, or not value, but mathematical operation in trig is cosine. We're not using sine, tangent, or anything else. We're going to use just cosine. So now we're going to use, it's pretty much theta is a small circle with a 0 through it. This helps students when they're trying to write theta. So let me see if I can tell you what theta is. Theta is like about the angle. So we're going in a rotation kind of like this here. Where is it at? Yeah. So when we're using circulate, there it is right there. I was trying to show you. It's a better view, right? This is the magnetic flux equation we're going to use, right? And since we have angles that are utilized for understanding what the B field does in correlation to the electricity, that's provided, we have to use theta, and that's what theta means, right? Theta is the angle. So there's theta. All right, let's get back to the work. So we got our conceptual meaning. This is just a definition, conceptual meaning or definition. All right, and all this down here is going to be your solution that you're providing. Where's that? So now that we have that part, we can pretty much reduce it down to what we need. Well, we need the magnetic flux. If we read the equation, I'm sorry, not the equation, the problem slowly with the values I provided, we have 2.57 centimeters. Ooh, make my corrections. Right? Radius is in a constant magnetic field. So what is that? Where do we use that? That's R, right? So let's break it out and do our unknown and unknown values. So what are we given? Given values. That includes what you're not given. You gotta ask yourself, what are they? This translates to, as I've always said in class, your known and unknown values. So what do we know? Unknown. What are we being asked? What don't we know? And that's easy to determine because we're just looking at what the problem is literally telling us we have. So let's go through it slowly. We have our R, we said earlier, or radius, which is equivalent to 2.57 centimeters, right? So this can also be converted, and it has to be converted because when you're using this equation, we're using just meters, right? Not centimeters. So we gotta be careful because we're already squaring our radius. We don't want to confuse ourselves. We want to use accuracy. I mean, the words are designations for whatever measurement you're looking for. The prefix is called. So how do we handle that? How do we just make it meters, this 2.57 centimeters? Well, if you understand what the word centi means, this is usually in your book, it's 2.57. And the word centi means times 10 to the negative 2. So times 10 raised to the negative second power, and that's meters now. Moving on, what else are we given in the problem? We have our vector B, or our B field as a vector. So vector B is equivalent to, and it says it in our problem set, 0.526 Teslas. Okay, getting halfway there with the known values. So we got a few angles. Each one of those, as I said before, we will consider to be called theta. So theta 1 is equivalent to 2.45 degrees. What else we have? We have theta 2, which is equivalent to, what do we say? It's up right here. It's 37.6 degrees. Theta 3, because we have 4 of them, right? Equivalent to 68.4 degrees. Oh, I gotta clean that up. And then theta 4, the very last angle they gave us was 97.6 Well, I should say I gave you guys 97.6 degrees. All right. I think we have everything, but what we don't have is what we're being asked. We had to define that so we know how to attack it. So remember earlier, they're asking for the flux, right? Find the magnetic flux. Let me zoom in for you. Right? So magnetic flux, I told you earlier, is always that symbol with the, let's go back to it for a second. Not that, but this symbol here. So when we're typing flux, just have that symbol in the forefront of your mind. That's exactly what I'm iterating each time we're doing this calculation. Okay, so let's move on. That means we have 4 fluxes because we have 4 angles where we have to calculate this. So we're going to say flux 1 is equivalent to some number in Tesla meters squared. We have flux 2, which will be equivalent to some number. Where's that at? And it's also a Tesla meter squared. And let's see if we can pull it off this way. And that'll be our flux 3. And we gotta do that one more time for our flux 4. All right, so this is 4 calculations. This is why this problem is a lot of credit. Now, what do we do? Well, we gotta take the equation we're given here, this magical thing, which is your tool to calculate the flux. So if we come down, we should start with that equation. So let's take the conceptual parts like magnetic flux and just put flux and vector B, area, and just what's necessary here, okay? So take this right here, copy that and put it down here. And this is the part where you take out, what do we say, flux. This is going to be flux, which is in Tesla meters, right? We'll leave that there so you understand it. Vector B is fine, that's what it is, but should by default take all this out. Okay, area is assumed to be that, right? And let's go through it. So looking at this, we have flux 1, right? So flux 1 is what I want. And now what are we working with? Well, that's going to be equivalent to, like I said, everything in this equation. So flux 1 is equivalent to what? Well, that's our B field. We said that was 0.526 Teslas multiplied by, and notice I'm putting in products so it stays neat for you. You put in a Google and Google calculator. So next we have our area, which is composed of pi. So let's put that together. That's 3.14 using that approximation multiplied by our radius, which we said was 2.57 times 10 raised to the -2, and this is in meters, which is going to ultimately be squared again. Okay, keeping it moving. And that's all included right there. Multiplied by, what else are we given? Cosine, and our theta In this case, that we're doing this calculation is theta 1, because we're using flux 1. So it'll be 2.45 degrees. All right. So that's one calculation. Now, how does that work when you're doing it for other degrees? Because that's one solution, right? So let's just take this, and I'm going to show you exactly what changes in each situation once you constructed this, the degrees. So same measurements, right? They go in where they are. But now we can actually plug in our next degree for theta 2. So that's 37.6. Let's not forget that this is now flux 2. We have flux 3, right? And I'm going to come to the end here. And flux 3 is based upon the angle you have at theta 3. So say for each of these degrees, this calculation has to be done again. Okay, we're done with that. Guess what I'm about to do? Flux 4. So flux 4 is done, and then of course that's based upon theta 4. It's 97.6. Okay, so what should go in between is just the answers for each. So let's do, all of them real quickly. And we're gonna use Symbolab for this part in case you're not familiar how to type it into Google. All right, I think it's a little safer and easier for you. So let's begin. We're gonna type flux. Well, I should have just copied it. Flux 1 is equivalent to, and I'm gonna take pretty much what I need. Like the dimensions are fine. This is great for your mathematical proof, but you still have to be able to know when to calculate with dimensions and whatnot. So does anything cancel out? Right? Doesn't look like it, right? But this all consolidates. The cosine of 2.45 degrees, that's just going to turn into some number. But when it comes down to these metrics here, is it true to our unknown values we wanted, which is a Tesla meter squared? This will become meter squared. That's a Tesla. They become together, and they actually give you what flux is supposed to be measured at. So just checking the dimensional analysis. We talked about that before. Next, we want to take the values we need. So let's see here. That's going to be, for instance, let's open up Symbolab. And this is a calculation from prior. We're typing in what? Well, we're typing in our B field, right? Or vector B. Let's go back to this real quick so you can see it. So that'll be, for our first calculation, 0.526. 0.526 multiplied by 3.14, right? That's our pi. And here, I think you can use pi, and it's in the corner right there. It's a good approximation of 3.14 multiplied by, right now we want to use parentheses because we have a whole lot with our 2.57 times 10. So you just group that by itself, 2.57 times 10, raise it to some power. In this case, it's -2. Okay, but you're not done with that because you still got to do what? You got to raise that to a power. That's what the equation said. It's pi r squared. Okay, you pretty much know what's going to happen with those exponents. If you don't, just stay safe and use Symbolab. Okay, so we're moving on. Multiplied by, well, I told you we had to use some other things, right? So I'm not mistaken. Where is this at? It's supposed to be cosine somewhere in there. I wonder if I could type it. Oh, full pad. That's the issue. Okay, there we go. So always just click on full pad. It'll give you the whole plethora of tools you can use. So cosine, and I think our first angle was 2.45. So that gives me a decimal value, which is negative, and that's fine because based upon how these values are tweaked, it'll be okay. As a flux, because it really doesn't matter about polarity. It's going to be, let's see here. I want to copy that number here. See if that helps you guys out. And nope, you can't. All right. So the first value, the first solution is a negative 0. What was that? 3084. So let me come back here. So that's a negative 0.3084. And this is measuring what? A Tesla meter squared. All right, let's move on to the next. I'm just going to take this and redo it for Flux 2. And this is not going to be the same answer. So let's see what we get when we use 37.6 degrees. Can we go back? Yes, we can. And I hope you can see from the screen share like how seamless this is, and what you do, just take your time and go through it. So the next value is going to be equivalent to 0.20108. So 0.00108. And let's see, was that negative? Nope, that was positive. We give it some more angle, some more degrees, it gets more positive. Start with 2.45, 37.6, it gets positive. Okay, let's move on. We have Flux 3 we have to consider. And what is that going to turn into? Well, we got to look at what it is. The degrees for this is 68.4. So let me see. This is going to be 0.3082. So 0.100, there we go, 3082. Last one. Then we can talk about the assignment itself. Flux 4 is going to be equivalent to, well, let's see here. I could have just pasted that, but I didn't. But the last angle, I think, was 97.6. All right, and what do we get? That's going to be a negative. So it's going back negative again. Negative 0.20106. So negative 0.20106. And that again is in a Tesla meter squared as a measurement. All right, so that's pretty much all you have to do, right? I went through a problem that's similar for you. You have to crunch the numbers similarly to get your answers. Type of the report as I have. I mean, not expecting anything of you, I can't do myself. Let's come back here to what is it? This is February 5th problem, right? And today I'm going to post a similar problem. It'll have slightly different values than what you saw me doing a problem, which means you got to go through it slowly and do it yourself and make sure you type it up. Okay. So if you got questions, concerns, you can reach me through ESB. I'm going to start closing down this video at this time because looking in the room, there really is not any students that came in. So I'm going to send the recording through ESB in a moment. So you guys can take advantage of that, go through it, very slowly, and see how you can get today's problem for Friday done, and also the problem on February 5th done as well, okay? The quarter's closing. I'm gonna say we have maybe 5 or so more days left. Please, please, please take advantage of this time to finish strong, all right? Take it easy and stay safe out there.